Welcome to this Concept Explainer, brought to you by CBSE ScoreLab of ProfSam.com. That is ProfSam.com. Today we're taking a deep dive into one of the most fundamental derivations in Unit 10, wave optics. We'll be focusing on how Huygens Principle mathematically proves the laws of refraction and reflection. We'll make it so clear you'll ace this in your exams.
Okay, so Huygens Principle, it can be a little abstract.
It can be. So let's start with something really simple. You must have seen it 100 times. You put a pencil in a glass of water, and it looks bent. Why?
Right, the pencil looks broken at the surface, and we know the textbook answer is refraction, but that's just a word, isn't it? What is physically happening? Why does the light actually decide to bend when it hits the water?
Exactly the right question. It's not just bouncing off water molecules or something. The real reason is, much more elegant. And here's where it gets interesting. Think about a diamond. Why does it sparkle so much? It's because of extreme massive refraction.
Because it's so dense.
Precisely. Its refractive index is very high, about 2.4. And this causes light to bend very, very sharply inside it. Our mission today is to show you that this bending isn't some magic rule. It's a direct mathematical result of light behaving as a wave.
So we're moving beyond the simple light ray idea from the last unit and thinking of light as a bigger picture, a wave.
Exactly. Forget those thin lines or rays for a moment. We have to start visualizing light as wavefronts. Now, a wavefront is simply a surface where every single point is vibrating in perfect sync, in the same phase.
Okay, a surface of points all moving together.
Perfect. And the core idea for today, Huygens Principle, says that every single point on one of these wavefronts acts like its own tiny source of new waves. We call them secondary wavelets. And the next wavefront is just the common surface, the tangent that touches all these little wavelets.
So it's like a chain reaction of waves creating the next wave.
That's a great way to put it. Now, for the best analogy, imagine a long column of soldiers. They're marching in a perfectly straight line across a smooth, dry field. This line of soldiers is our plane wavefront. And they're moving at a certain speed, let's call it V1.
Okay, I'm picturing it.
Now, at an angle, they approach a big patch of mud. That muddy field is our denser medium, like water or glass. What happens the moment the first soldier on the end of the line steps into the mud?
He'll slow down, obviously.
Immediately. He slows down to a new speed, V2. But, and this is the crucial part, the soldiers still in the dry ground are.
Still moving at the old, faster speed, V1.
Yes, so you have one end of the line moving slow and the other end moving fast. What must the line do?
It has to pivot. It has to turn.
It has to turn. The speed difference forces the entire wavefront to rotate, to bend. And it bends toward the normal. The Y is purely mechanical. The speed change makes the bending completely unavoidable. This is the mechanism that Snell's law just gives us the formula for.
I see. So the mental image is like a door. The edge that hits the mud is like the hinge, and the rest of the line just swings around it.
Perfect image. And that's why this was such a huge deal. The old theory from Newton's time, the corpuscular theory, it also predicted bending. But to explain it, Newton had to assume that light speeds up in water. Huygens' theory predicted the opposite, that it must slow down.
And when they finally measured the speed of light in water,
They found it was slower. A huge victory for the wave model. The speed changes everything. Okay, let's get into the formal exam-safe derivation now. First, let's see the formal relationship for the refractive index. N, could you read it for us from the source material?
yes. The refractive index, N equals C divided by V, where C is the speed of light in vacuum and V is the speed of light in the medium.
Excellent. So high N means low V. Now, for the derivation of the law of refraction, picture a plane wavefront, let's call it AB, hitting the boundary between medium 1 and medium 2. The speed in medium 1 is V1 and medium 2 is V2. The whole proof is built on one simple fact. We consider the same interval of time, tau, for the entire wavefront to cross.
Okay, so time is the constant.
Exactly. So step 1, look at point B on the wavefront. In time tau, it travels to point C on the boundary. So the distance BC is just speed times time, or V1 times tau. Step 2, now look at point A. It hit the boundary earlier. And that same time tau, it starts a secondary wavelet inside medium 2. The distance that wavelet travels, AE, will be d times tau.
So the distances BC and AE are covered in the same time, but because the speeds are different, the distances themselves are different.
You've got it. That's the heart of the geometry. Step 3 is just to draw the new refracted wavefront. It's the tangent line, CE, drawn from point C to that little wavelet from A. And now for step 4, the simple trigonometry. We have two right-angled triangles. In the first triangle, sin of the angle incidence, I, is opposite over hypotenuse, which is BC over AC. So sin I is V1 tau over AC.
Okay.
In the second triangle, sin of the angle refraction R is AE over AC, which means sin r is v2 tau over ac. Now, what happens when we divide the first equation by the second?
Well, the AC on the bottom of both,
Yep.
it cancels out.
Yep.
And the time tau also cancels.
It cancels out beautifully. And we are left with the fundamental result. Sin I over sin r equals v1 over v2. This equation is the proof. It shows that if r is smaller than I, which is bending towards the normal, then v1 must be greater than v2. Light has to slow down.
That's fantastic. So the ratio of the signs is just the ratio of the speeds.
Yeah.
How do we get to the familiar Snell's law with the n values from this?
Simple substitution. Since v is c over n, the ratio v1 over v2 becomes n2 over n1. We substitute that in, cross-multiply, and we get the famous law. Could you read the final insert statement for us?
Certainly. In terms of the refractive indices, EQ 10.3 can be written as n1 sin I equals n2 sin r. This is the Snell's law of refraction.
Perfect. And remember, when this happens, speed and wavelength both decrease.
Yeah.
But the frequency of the light, it stays absolutely the same. Hope everything is clear so far. This concept explainer is from ProfSam.com. That is PROFSAM.AS, Tom. Now, very quickly, the law of reflection. This is much, much simpler.
Why is it simpler?
Because the wave hits a mirror and bounces back into the same medium. The speed doesn't change. So the wavefront AB hits the surface. In time tau, point B travels to C. The distance BC is V times tau. In the same time, the wavelet from A also travels a distance AE, but since the speed is the same.
The distance AE must be equal to BC.
Exactly. AE equals BC. Because of that, the two triangles we form are congruent. They are identical.
Huh.
And if the triangles are congruent, then the angle of incidence, I, must be exactly equal to the angle of reflection, R. It's a direct geometric proof.
So no ratios needed, it's just simple geometry.
That's it. Okay, let's do a very quick numerical example for refraction, just to be sure. Say light goes from air, where n1 is 1, to glass, where n2 is 1.5. The angle of incidence I is 45 degrees. We know it's going into a denser medium, so the angle R must be
Smaller than 45, it has to bend towards the normal.
correct. So we use n1 sin I equals n2 sin R. That's 1 times sin 45 equals 1.5 times sin R. Sin 45 is about 0.707. So sin R will be 0.707 divided by 1.5.
Which is about 0.47, a smaller value, which means a smaller angle.
Right. It comes out to about 28.1 degrees, which confirms our rule. And this leads to one last crucial idea: total internal reflection. This only happens when you go from dense to rare, like glass to air. As you increase the angle of incidence, I, the angle of refraction, R, increases even more because the light is speeding up and bending away.
Okay.
Eventually, you reach a special angle, the critical angle IC, where the refracted angle R becomes 90 degrees. The light just skims along the surface. If you put R equals 90 into Snell's law, sin R becomes 1. And you find that sin of the critical angle, IC, is simply N2 over N1. Go beyond that angle, and refraction is impossible. All the light reflects back. That's total internal reflection.
So even TIR is just a mathematical limit of Snell's law, which came from Huygens' principle.
You see, it all connects.
Right.
Ray optics gave us the rules. Wave optics gives us the reasons. Okay, now for the part that saves marks. The silent killers. The common misconceptions. Killer mistake number 1. Students think light slows down because it's, bumping into atoms, like a ball in the pinball machine.
I can see why people would think that, but that's the wrong idea.
Totally wrong. The correct idea is much more about electromagnetism. The wave interacts with the electrons in the medium. It gets absorbed and immediately re-emitted over and over. This continuous process of interaction slows down the overall pattern of the wave. We call this the phase velocity. The energy is conserved, but the wave pattern travels slower.
Okay, so the memory hook should be, it doesn't slow down by bouncing. It slows down by interacting and re-emitting, which reduces the phase velocity.
Perfect. Killer mistake number 2. Confusing the direction of bending. The rule is simple. Slower medium, bend toward the normal. Faster medium, bend away from the normal.
So let me restate that to be sure. If light goes from glass out into air, it's entering a faster, rarer medium, so it speeds up and bends away from the normal.
You've got it. And the final killer mistake, back to Huygens' principle itself, the idea that wavelets create a backward wave.
Because the definition says they spread in all directions.
Right. But the correct idea is that while they do spread, the new wavefront is formed by constructive interference. And that only happens in the forward direction. The backward wave is canceled out. So the memory hook is, Huygens' principle works because the geometry only allows for forward propagation.
Okay, that's pretty clear.
Good. Now for some final memory anchors to make this all stick. Remember the mnemonic SNDR. S for speed change, which causes everything. N for bending relative to the normal, D for what happens in a denser medium, and R for the refracted angle, SNDR. The phrase to remember is enter glass, slow down, bend toward. Exit glass, speed up, bend away.
I like that. It's simple.
And finally, the physical gesture. Hold your hand flat like a wavefront. As you move it forward, touch the edge of your desk. As your hand hits the denser medium of the desk, let it pivot inward toward your body. That pivot is the refraction. You can feel the bend.
That's a great visual.
All right, to wrap up, let's go over the 3 most important factual points from today. Point 1. The laws of refraction and reflection are not just rules. They are mathematical consequences derived directly from Huygens' principle and the change in wave speed. Point 2. When light refracts, its speed and wavelength change together, but its frequency, which is set by the source, remains absolutely constant. And point 3. Total internal reflection is explained as the geometric limit of refraction, defined by the critical angle, sin IC equals N2 over N1. To get maximum marks in 12th CBSE Physics, Chemistry, and Maths, visit ProfSam.com.
That is ProfSam, right?
Yes, ProfSam.com. Thank you for joining us on this deep dive. We hope this makes the derivation much clearer.